So let's start. It's 11:30 Eastern time. So let's start the session. Hello, everyone. This is a HDF Town Hall session at the ECIP summer meeting. This is my first virtual ECIP session that I'm going to host, so please bear with me. But hopefully we have enough support staff and everyone else to help me get through. The agenda for today, we have 90 minutes and we have 5 presentations, so time is of essence. The agenda is, we'll start with Elena Purmal, which is our Director of Engineering, and she will update you on the HDF5 latest developments and where HDF5 and ecosystem are heading. Then we'll continue with Michael about stair pods. It's an interesting new development that uses a fairly new and interesting feature of HDF5. And then we will continue with our own Joe Lee, who is going to present a use case using Apache Drill and Threads data server for accessing NASA HDF-US data on S3. And following that, John Reedy, our cloud architect, who's going to again present the latest developments about HDF in the cloud. And then the latest addition, which is embarrassing to tell when it was added to this agenda, let's say last night. I'll talk about connecting HDF5 and ZAR so that each one of them can read each other's data. And so with that, the only other thing is I will be monitoring the, oh yes, I forgot. But then let me finish with the chat thing. I will be monitoring the chat window, and so any questions that are asked during anyone's presentation, at the end I will read out, and the person who gave the presentation will answer. And also any other questions or follow-ups, I will try to ask them at the end of the session. The final announcement before we begin is that HDF5 is now an officially OGC standard. All the paperwork, if you will, was done last year, but somehow the official announcement by OGC was delayed for quite a few months, and I think went out maybe 4 or 5 weeks ago. So I just wanted to bring this to anyone's attention who joined this session. I'm personally very excited about this because it presents a foundation now that we can go and start defining and creating various encoding standards using HDF5 for other OGC geospatial standards. And with that, I will stop sharing and I will invite Elena to share her screen and start the first presentation. Elena, the virtual floor is yours.
Okay, can you hear me now and can you see my slides?
Yes.
Okay, thank you. So Alexander, thank you for introduction, and hello everyone. I see old friends in the audience. Very nice for you to come to our HDF Town Hall. I will be, let me figure out how I check slides. Okay, so I will give I hope, very brief presentations to allow more interesting stuff to come up. I will talk about HDF updates on HDF software, releases, new features, and our community engagement, and update you on two very interesting developments that are happening in HDF5 ecosystems about 2 new packages that we're working with those developers. Okay, with the releases, just brief mentioning of HDF4. HDF4 is deprecated software in favor of HDF5. We do not have releases very often. We usually release it once a year, and the last release was in February 2020. And very little is going on there. We just keep up with the platforms and compilers. and we're doing some code cleanup just to keep code in healthy state. We have for quite some time problem with porting software to new Mac OS systems. Finally, we resolved the issues, but we're anticipating more and more troubles because, for example, we know that we will need to completely rewrite Fortran library to work with new GCC compilers. So I appeal to you, if you're still using HDF4, migrate to HDF5 right now. There is H4 to H5 tool software that can help you to write programs, conversion problems. It also comes with the tools that allow you to convert HDF4 files to HDF5 files. So HDF4 will not last forever. Please, if you use it, go to HDF5 now. So with HDF5, we have three major lines of maintenance releases, 1.8, 1.10, and 1.12, and it can be a little bit confusing. So one thing I want to mention about all releases, we address in all of them, when applicable, vulnerability issues reported by HDF5 community. And if you're watching those vulnerability issues, I want to explain to you that those come from people intentionally modifying HDF5 files outside HDF5 library, introducing errors in HDF5 files. And unfortunately, HDF5 library not always gracefully exits. It may crash, it may issue some errors. So it is good that people report it, but those really not vulnerability issues you really should worry about because someone intentionally modified file. If you have checksum on your files, you will know that file is modified. But we're addressing them in 1.8 and 1.10 and 1.12 releases. Our 1.8 release was last time almost more than 2 years ago, and it includes some small bug fixes, updates to C++ APIs, but not much. We really, software is very stable. We're not bringing any new features to it, and we're planning new release late in this year. So please consider migrating to 1.10.6 or 1.12 unless you have some performance degradation problems what you experience when you compile your application with 1.10 and 1.6, 1.10 or 1.12. We are going to drop 1.8 releases as soon as we address performance issues in 1.10 and 1.12 releases. Those performance issues are related not to one particular change, but 1.8 is more than 10 years old. There is a huge difference now in the code base of 1.8 and 1.10 and 1.12 releases, and all new features added here and there a little bit, 1-2% of degradation. And we now have to go and clean up, and we probably will not get to the level of 1.8, but we're trying very hard to come at least within 10% of 1.8 performance. And as I said, it doesn't affect every application, so try it. And if you don't see any performance problems, I encourage you to move to 1.10.6 or 1.12.0, which are latest releases. So in December 2019, we released our latest 1.10.6 release and 1.10 series, and we added 2 new virtual file drivers, 2 I/O drivers that allow you to access data in the cloud and on Hadoop file system. More about this 3 will be on the next slides. We also improved performance when creating a large number of objects. This is our work toward reducing the performance gap between 1.8 and 1.10. And 1.10.6 is the first release that we can tell for with very high confidence that we addressed all compatibility issues with the previous file format. So if you create, your application have full control on creating files that are fully compatible for applications that are were written for versions of HDF5 library 1.8 and earlier. New release is coming. We are almost in code freeze, and we are putting more performance improvements for handling large number of objects. But what is new, it's performance improvement that first was introduced in 1.12 for handling selections when you work with big data sets. So we see for 20 gigabyte data sets, when we need to do selections, several order of magnitude performance improvement. So if you're working with big files, if you're working with selections, 110 or 112 are your candidates. 112, it was a major new release that was released recently. It has two new features called virtual object layer and external references. So virtual object layer allows you to talk through HDF5 APIs to different type of storages and different type formats. And we'll see on the next slides how we use virtual object layer, and in John's presentation probably how you can use a RESTful to access HDF5 data in cloud. External references, this is a new feature, and it's introduced updates to file format. So if you use this feature, your files will be not compatible with 1.8, but you can always use H5 repack tool to downgrade to the file format that can be read by 110 and 1.8 earlier. So why we encourage you to move to 112? If you're 1.8, maybe it's a good idea to skip 110 and go to 112, because performance between those two almost identical. First of all, because 112 introduces multiple ways to access data in cloud and in object store. And there are multiple capabilities. You can use new virtual object layer or our old existing feature, virtual file drivers. See on the next slide, I will show you. And what is nice about those features, that minimum or in case of wall, no modifications are required to applications. External references is a really new powerful mechanism that, along with introduced in 110 virtual data sets, provide a very flexible way to aggregate data stored in HDF5 files. So you can have one file that really points to different files, different objects in the files, attributes. So when you're handling collections, you may start building aggregations so that for your users it will be easy to see all relevant data. And as I mentioned, there are a lot of performance improvements in sequential and parallel HDF5 library if you're interested. So this slide represents a new architecture in 112. I should mention here that with this new architecture, all changes that we're making to the library and all capabilities we're adding are immediately available to language wrappers and to software that is built on top of HDF5, especially when no modifications are required. So the very high level, very top level, it is HDF5 APIs and language bindings, or application sits on top of that. And then virtual object layer that sits exactly under the layer of public APIs. It captures calls from the application and it redirects the flow through another layer, which is called pass-through connectors, to external connectors that talk to different type of storage. Those are external, those are not part of HDF5 library. They come as all libraries and they are dynamically loaded at runtime. And among those different wall connectors that are developed by us, like RESTful and DevSful, you can choose how to talk to different storage. For example, RESTful, you can talk to cloud storage using HSDS server that John will be talking about. We're also creating Deos wall connector, which will allow us to talk to Deos file storage that will be available. It's open source type of object store that will be installed on new Aurora exascale system that is coming in Argonne. And there are many wall connectors developed by a community like Data Elevator or Hermes to talk to different memory storage devices and different devices and file formats. We provide the common place where all wall connectors are gathered. So if you are interested in sharing, and if you are interested in better maintenance in terms we can test your wall connector, talk to us, and maybe you will decide to move your connector to one repository, so users have access to all connectors in one place. The old mechanism to talk to storage was through native library. Now we call it native connector or HDF5 core library. And native HDF5 core library does I/O, talks to storage through different file drivers. And originally we have POSIX file driver, MPO file driver. Now we're developing new driver that is called single writer multiple reader driver, which is different from the feature we have in the library. It's really will be pluggable and resides in it can be loaded during runtime. And S3 driver that talks to data stored in the cloud. So you may ask me, what is the difference between the drivers and wall connectors? So HDF5 VFDs or virtual file drivers, they treat the file as logical space, as logical file that complies with the HDF file format. So a virtual file driver knows only about offsets and length of number of bytes that go in some location in the file. So S3 talks to HDF5 file that is stored as an object in S3. This is different from wall connector that really is in charge how data sent by HDF5 application is organized on the storage. And John with rest, I'm sure he will show how it is done. But for example, wall connectors can be used to talk to data in ZAR format, in netcdf format, and there are connectors already developed by, say, Argonne to talk to netcdf files, which is a standard 64-bit file, netcdf file, and so on. So wall connector can organize data in any way that is more beneficial and more performant on the storage versus original HDF5 file format. So now we have those two very flexible mechanisms to access data that HDF5 application put into storage. This is as an example to just give you a flavor how you will use it. So as I mentioned, S3 virtual file driver is a part of 1.10.6 and 1.12 releases. It should be configured when you configure the library by specifying a flag to configure CMake, and it is read-only now. Usage is very simple. There are just new data structure where you specify credentials to access cloud, maybe password, so it's stored in this new structure or read-only S3 FAPL. And then according to HDF5 programming model, you just tell the library that you want to use the driver using this new API to open the file, and then no changes are required. So future work, we would like to improve scalability, and there are many different ways how we can improve it. The reason S3 is slow, exactly the same reason as it may have been slow on POSIX file system.
15 minutes, Elena.
Oh, okay. And for external plugin, this is the part of the code you have to initialize plugin, set FAPL, and go on. Or you can just set tell application without any modifications where to find, and you're done. Since I'm, how many minutes I have? 5?
Let's see, maybe that's too much, maybe 3.
Okay, 3, okay. So I will skip the slides. You can find that explanation of external references and explanation of references to attributes. What is coming? There are 2 more VFDs are coming in 1.12.1 and 1.12.2. It is called splitter and mirror VFD, where one can write and read file on the local system and send and write file on the remote file system, currently using TCP/IP protocol. And on the remote system, multiple readers can come and read that file. Another driver that we are introducing is provenance or onion driver. We're introducing version of HDF5 file when you modify the file, changes to the file are stored within the file, and there are library capabilities to retrieve any change to the file that was performed between file open and close cycle. A few words about upgrades. So first of all, we are moving to GitHub. It will be announced. Right now, GitHub repository is just synced with our Bitbucket, but stay tuned. We will go into GitHub. We're also working on our documentation. And if you are interested in contributing, gathering requirements, please look at this slide. And this is on HDF5 Wiki. Go there and leave us your comment. You can participate if you want to learn more. There are links to our webinars. There will be users group meeting in the fall. If you are interested to present, please contact me. And just 1 second about two very powerful new development in the community. First, there is a package called HDF Query Language. It's available on all platforms, and you can compare the code that you need to write using HDFQL comparing to HDF5C code, for example. What is important, this language has data and metadata querying capabilities. And another one is new development in H5C++. If you are interested in using H5C++ APIs, please use not ours, but use interface developed by Steven Varga, our collaborator, and you can find it on those links. And this is, you can compare the first high productivity language, H5Py and H5CPP codes, very similar, but H5CPP doesn't have any overhead, performance overhead, and it's very well integrated with most of C++ libraries. And with this, I will finish. Thank you.
Thanks, Elena. Any questions? I haven't seen any in the chat window, so if someone wants to speak now or not, and then we can move on. All right, I don't hear anyone. So we can move to the next speaker, that's Mike Riley. Mike, Elena, yeah. Okay, so yes, Mike can share the screen. Okay.
Very good, thank you.
Go ahead, Mike.
Very good, good morning. My name is Mike Riley, and today I'm going to be talking about the spatio-temporal adaptive resolution encoding, also known as STARE. And there's a good deal of teasing in this particular one because the STARE has been developed under the NASA's Access 17 project, but STARE pods, a parallel optimized data store based on STARE and in various HDF technologies, has been proposed to Access 19, and so that's the tease part. The idea behind STARE pods is to provide for scalable analysis-ready data, and that's scalability in both volume and also variety. And so I'll explain the variety term a little bit later. But basically it comes down in earth science, we have very diverse low-level data, and sometimes the science we want to do actually requires us to use the data at the highest resolution that we can get it. Sometimes level 3 or interpolated products just don't work. And STARE is a way to index data. It provides a unifying index that allows different kinds of data to be brought together. And once you have that, STARE has some properties that are good for bringing that data together, and in particular for the way that you can parallelize the data. So you have an indexing that is both good for geographic information, but it's also good for working in the cyber domain as well. One way, we have an installed base of tools and libraries and methods that we use, and a lot of that is based on HDF. And so what we're proposing in StairPods is to provide a layer where you can look at the data organized using Stair in the parallel store, but you get to use your existing tool sets and methods by operating through the virtual data set and object layer technologies. So the fundamental point is that StairPods would unify your access to the diverse data with a minimum of unnecessary copying and duplication. So first thing I have to do, I have to explain Stair, since it still is a relatively new concept. Basic problem is we have different kinds of earth science data that we want to bring together for our analyses. And that leads to some fundamental incompatibilities, because once you look at the data in detail, you have a mismatch between how you interpret the native array layout across different data sets. So here we've thrown up a grid which is indexed via native indexing L and M, and then swath. It has its own array format with index I and J, and then you have point. And this can refer to spacecraft data, in situ data, drone or aircraft. All of these data we'd like to bring together and make useful for our scientific analysis. Now, if you're going to be dealing with the data at its best resolution, then you have to go from the native array to the geographic interpretation. And that means you have to get very intimate with the data, and that can be expensive and slows things down a great deal. So for example, if I have two swaths, swath A, swath B, they have their native layout in memory, and I want to scale this up in volume. Well, the normal way that you would scale things up is that you would partition and distribute the memory layout of these different swaths. So for example, on the right-hand side, you can see that we've taken some storage or compute resource, named it 1, 2, or 3, and have cycled through a partition for our two swaths. And the problem is that when you bring them back together and you want to compare them, you see that the layout, the parallel layout on swath B does not match the parallel layout on swath A. And so immediately you've broken your scalability and volume. So because you have to do extra communication to bring that data together. And so that's a very important thing. Really what you'd like to have your data laid out in your arrays in a way that satisfies both geography, geospatial to temporal location, and on the compute and storage resources themselves as well. So what we do, we take an old idea. This comes from the hierarchical triangular mesh that the astronomers put together for NASA a while ago. We can use a recursive spatial quad tree. We start with a tilted root polyhedron and then project the edges of that polyhedron up onto the sphere. So we're actually partitioning a solid angle, and we tilt it so that the projected edges don't fall on common fiducial marks like the equator and poles or meridians, and that helps us reduce the ambiguity in the system. And then what we do is that we get the quad tree part by taking each of the triangular regions or trixels and then dividing them up by 4 in a very straightforward way that simplifies and helps make the geometric calculations efficient. We have, and then we encode each of these triangles with 64-bit integers. Now, the Stair temporal indexing is very similar, except that it's based on calendrical periods, and so you don't have a nice quad tree. You have a tree with different numbers of branches at each of the calendrical levels. So we have the hierarchical triangular mesh, the HTM. We have the hierarchical calendrical partitioning, HCP. And we construct an integer, a number, an index value for each triangle, depending upon where it falls in the tree structure. And so we just go from left to right, setting bits depending upon which branch we're going down until we get all the way to the 27th level, where we have a fundamental resolution of about 8 to 10 centimeters for a 64-bit scheme. Now, 27 for spatial representation, the 27 levels leaves us some extra space. And so for the rightmost 5 bits, we actually keep level information, which tells us about the neighborhood of the point location that we have. And so that way, for one of these particular stair spatial index values, we have both position information and area information as well. And we can use that for our set logic and finding things and finding neighbors for figuring out what goes where when we're parallelizing and distributing our data. So this helps with variety because our index value now actually has geospatial temporal semantics. And so if you have some data which is associated with one part of the Earth, and there's another piece of data which has a completely different native array indexing, completely different scheme, but it's also associated with that same place, it'll have a very closely related integer index value, and you can very easily tell whether or not you have overlap between those two regions. Now, this helps with parallelization and distribution. Down below, you can see the different colors. We can just map the different numbers which correspond to different regions of the Earth onto different compute and storage assets. So if I'm in the cloud and I want to spin up a bunch of instances, I can actually assign different parts of the tree to those different instances. And now I know where I'm going to put the different parts of the analysis data that I want to use. So now one point here is that, well, okay, do I really have to be a stair ID expert and understand what all the bits mean? No, not so much. We provide a library Python interface, so you can work with it through the API, a lot like you already work with the floating point values through an API as well. Here's an example. Here's a point in I believe it's Upper Mongolia, human readable form, single point of floating precision in hex, and then the same point in stair, except also in hex, except that the stair ID also has an aerial interpretation as well. So it's talking about a triangle that's actually about 10 meters on the side in those 64 bits right there. And on the right, you can actually see some of the tree structure, the recursive refinement of the triangles down towards that location around that pink dot. So there's a cost when you're going from level 0 to level 1, and you're actually constructing those latitude and longitudes to begin with. There's actually a cost in going to latitude and longitude. There's also a cost in generating the stair ID as well. So you want to make sure that you're comparing apples to apples when you're thinking about how much compute time it actually costs to make these things. Important point here is every index value is associated with a particular region or particular area. So that tells you that you can actually adapt the index, that you can actually adapt our stair indexing to the resolution that's in the data itself. So here we have a MODIS granule. You have a cross path scan, and on the right we have a subset of the nadir data, and then out towards the wing, you can actually see that the observation, the points associated with the instrument field of view, are actually spread out compared to where you have them on the nadir. And you can see that the nadir resolution represented by the squares isn't really a good representative of the resolution that you're getting out on the wing. Note that with the stair spatial indices, it just adapts to the resolution that you already have in the data as well. And this is a very easy to do with the stair system. Thank you, Ko, for watching the chat information there and providing some information. Here's just an example. Suppose I'm interested in Hurricane Irma, and these data here were actually taken from a forecast of Irma's track and size. And the larger triangles that you see there, they're actually 2 spatial dimensions plus 1 in time. And so you see the Hurricane Irma, its path in space-time as it moves towards Florida over there. And the size, the resolution level, the neighborhood level of the different triangles are actually indicated by the size that you have there. And then there's a notional little sensor which is orbiting around Key West over there. And so you can see that there's a different resolution level associated with that. And you see its motion. Key West doesn't move in WGS84, and so you see it just sort of stays in one place. So you can use that. So you can use that for your index querying. You can use that to collect data and co-align data. Now, this comes back to the point I want to make about parallelization, because once you have your data indexed according to the STAIR scheme, now we can talk about distributing this across compute and storage resources. And to give you an idea about that, here is a notional 16-way partitioning of a particular granule. This is an OMI granule path. It's a dayside pass of the spacecraft data. And each gray color over there corresponds to a compute or data storage resource that you would actually have the data associated with. And so this is a way that you can actually start to distribute and work on the data and scale up in volume. And because each of these triangles has the same index value or ID for all the different data that you've indexed, it also scales in variety. Another example, here we have GOES and MODIS data. On the left, you see a GOES Northern Hemisphere footprint and a MODIS granule. And you notice that the triangles are laid out on top of each other. You grab the data, and then you can co-align it into bins according to the STAIR indices. And that's what we've done over on the right and in the center. The blue is for MODIS and the brown is for GOES. And here, what we've done is that we've actually set the color of a certain size STAIR triangles. So we have all triangles we have triangles at the same level, same resolution, and now we're coloring them according to the data that's associated within them. And so here you have an actual fusion or integration of GOES and MODIS data into a single product. And so that one was variety. Now we're coming up to volume. On the left, we've colored the different level 5 STAIR triangles according to a notional storage or compute resource. And there you see we have our parallelization, and we're scaling up in volume for that. So that's all very good. We've indexed our data. We have it set up for multiple data sets. But now all my tools are not using STAIR. They're using HDF and linking to the data using HDF. Well, how can I get back to STAIR? And that's one thing that we've been doing some experiments with and have actually proposed as an Access 19 project, is to use virtual data sets in the virtual object layer to reach in to this data organized using STAIR and make it available to the tools that I'm using right now. So this is roughly the idea. We probably wouldn't have too many levels of redirection here according to this note, but it gives the idea where at the top level where I'm using it, I'm plugging my tools in. That's where I'm using my virtual data set API to reach into the system. And then down below, I have my data cut up into these STAIR trixels. And this could be individual. Each one of these little round marks over here is a high resolution instrument field of view observation. But down here, I've chopped things up into STAIR partitions, and that's where my storage layer is. And that's where I get the name scalable, homogenized, analysis ready data store. So I have lots of data indexed according to STAIR, and then I'm going to make it available to your regular tools through the HDF virtual data set. So if I'm coming in and my methods know how to work with a virtual granule, then I can figure out what STAIR indices cover that granule. And then I can start to piece together a virtual data set which reaches back into the data source to actually provide data through the existing mechanism. And the idea is that using the virtual object layer, I can use a variety of ways to actually store this data on the back end. Michael. So here you see I have a number of different data. Thank you for the timing. So here I have data source 1, 2, 3, A, and B, which brings us back to where we started with, where I had two swaths and I wanted to bring them together. And so this is how I would bring them together. I have them split in and parallelized according to the STAIR indices. and then I bring them together using the HDF methods to actually get the variety scaling and scale up. This is the proposed architecture. It's pretty much what we've already been talking about: computing and storage options down below for reaching out into the cloud, or perhaps if you're in a high-end computing environment, you could do that as well. Indexing and organization with the store, and then bringing it up and making it useful. One thing to note is that we're actually adding, as part of the Access 17 project, some stair awareness to OpenDAP. So pretty soon, OpenDAP itself will be able to help provide you stair-based queries. So if you're an OpenDAP user, that's going to be an interesting possibility to look at. One thing to note is that rather interesting development in our analysis of this problem is that once you have a unifying index for all of these data, it makes sense to start talking about a stair location service, sort of a DNS for geolocated data. So the idea being is that if you have a particular geospatial temporal region that you're interested in, you can then go and bang on the stair location service, and it can start to give you idea about where those things actually are in cyberspace. Except that you don't necessarily need to know the actual IP addresses or some of the lower level information, much as an analogy to the way that we work with the internet today. So in conclusion, this is our idea that we have the T's for stair pods to integrate your data in a scalable fashion for both variety and volume. It's based on the stair indexing that we've been working on for the past 2 years. There's, as with anything, there's a cost in actually calculating the geolocations, but we're coming up with stair sidecar files so that you only have to pay that cost essentially once. There's an interesting OpenDAP integration in progress. We have a growing set of libraries and cookbooks at Spatiotemporal. It's very interesting. Some of them are less mature than others, but it has some interesting examples over there that you can play with. And finally, for the next, where we would hope for this work to go, is with the development of stair pods and stair shards, where we can organize our data according to stair, put it on the cloud, put it in high-end storage device, organize it using stair, and then provide it using existing methods and tools built on the new HDF object layer and dataset technologies. So Alexander, that concludes the talk.
Thanks, Mike. I was following the chat window activity, and I think that the only question not answered right now is from RKC that says, are the data in the Trixel nodes oriented to allow for post-process 3D rotation, or are they pre-rotated to a reference?
So are do
you see it in the chat window? It's 12:07 p.m. timestamp.
Yeah, I wasn't clear if because I see that the triangles have a certain scale and position on the globe. But when you have a swath or any kind of data sample, you have all kinds of compass rotation and tilt and so forth that's worked into that data. Does that all get remapped in stair to a single reference?
Currently, stair is based on WGS84. So when you think about the spatial component of that, we're built on the WGS84. We're partitioning the solid angle. And so there's actually very little that we're doing. So one way to think of it is that we're at the same level as latitude and longitude. So the sort of things that you're talking about are not something that at the basic level we're dealing with our indexing, which is meant to organize our data in both geophysical space and in computing space. So that's my first answer at this level of understanding of what you're asking.
Yeah. Thanks.
If you'd like more detail, we can discuss that later if you like.
Yeah, this is really great. Thanks.
Thank you.
Hello, this is Quo. Can you hear me?
Very, very quiet.
Oh, okay. Is this better?
Yes.
Okay, I like to chime in. People usually get hung up with those triangles, but the triangle, those divisions is only to partition the solid angle or the geolocation. Okay, that doesn't mean that the pixel is a triangle. You can use it as a mesh, as a grid, yes, but we are not using it as a mesh or a grid. The partition, it's only used as a partition, and it refer, just like a floating point latitude longitude, it has precision too, depending on if you use 32-bit floating point, or you use double precision floating point, you have a precision. So the triangle, the size of the triangle defines the precision of that pixel at that index level. So don't think of them as representing a pixel or a grid cell. It's simply used for indexing the latitude and the longitude, the geolocation. But we used, as Mike mentioned, we used leftover bits to indicate a neighborhood, which as our remote sensing data have resolution. So we use that to indicate qualification level that's compatible with the data elements resolution. And then, when we are doing subsetting, overlapping, different resolutions, data of different resolutions, and we get the set operation, get a better result. Okay, I don't know whether that makes sense to the original people who asked the question.
Or we have thank you with +1. So that's
okay, all right. Thanks.
Useful. All right, thanks. If no more questions, then we move on to the next presenter, which is our own Joe Lee. So Joe, yep, all right.
Hi, my name is Joe Lee, and I'm a software engineer at the HDF Group. Although my job title is software engineer, my primary duty is to satisfy every user who wants to do something with the NASA Earth data in HDF. Such user can be a kid who wants to play Minecraft navigating North Pole terrain map from ice data, or a senior who wants to play calm music from ocean data using Alexa. My goal is to make data access easy so that everyone in the world can enjoy NASA Earth data in HDF. Since this meeting is virtual due to pandemic, I decided to make my talk easy to listen at home with your children. Feel free to take off your headset and listen to my story on a loudspeaker with the maximum volume. Once upon a time, there were 3 little pigs called Drill, Dress, and Butcher. They were the children of the smart mother pig who made the bad wolf fall from chimney and die in a brick fireplace. All 3 little pigs were smart after their mother, but each pig went to a different school. Drill attended Apache, Dress attended Unidata, Butcher attended the HDF Group. All 3 schools joined the conference called AWS that competed sports called Hackathon against other schools in Azure, Google, and Alibaba conference. Since the bad wolf is gone, the pigs ate all the foods on their land called Hadoop and became very big, too big. There was almost no food left on the field in Hadoop land, so mother pigs sent them out into the world to seek their fortunes. One day, 3 pigs heard a rumor that there are unlimited amount of food available in the new land called S3. The name of food was highly delicious food, or HDF in short, because it was produced by high-quality manufacturer called National Animal Supply Agency using a scientifically proven formula. Highly delicious food was not only unlimited in quantity, but also available in 5 different flavors: 4, HE2, 5, HE5, and NC4. Although flavor 5 and NC4 are produced from the same ingredient, young pigs like flavor NC4 more because it's easier to digest, while older pigs still prefer the flavor 4 with grown-up taste. Red hot flavor 5 was very popular among pigs as well, as are the clever animals like pythons and hyraxes. Even AI robots that can learn and act like real humans enjoyed eating highly delicious food at night in a cafe decorated with bright torches. However, the most other creatures could not taste HDF because it was shipped in a hard sealed container like a shell for long-term preservation. After hearing the rumor from Hard Land, 3 little pigs had a discussion on empty dinner table about S3 land. The first pig, Drill, asked, if there are unlimited amount of highly delicious food cans, how can you store them properly? The second pig, Thread, said, we definitely need a bigger house than we have now. The third pig, Butcher, said, then let's build one in the sky on top of a cloud, since the earth has stopped making land anymore. The first pig, Drill, came up with a big house plan that uses hay called SCALABILITY and a glue called HDF5. SCALABILITY was a very light material for construction, but it was available from anywhere. Drill could gather a large amount of SCALABILITY and build a big house to store the unlimited amount of highly delicious food cans. The good thing about hay and glue was that Drill could also build any furniture like a table. To build a house that lasts forever, Drill finished the house with a premium hay called NCS12. And NC was the most popular among house builders. After finishing the house first, Drill started storing some HDF cans into tables. Unfortunately, Drill's table could store only HDF flavor 5 cans. Drill's house was quite scalable too. It could store thousands of HDF5 cans without any problem. Using the tables, Drill could sort the HDF5 cans by manufacturing date, although Drill could not identify where the food came inside HDF5 cans. The second pig, Threads, who studied at Unidata, took a different approach from Drill. Threads built a house with sticks. The sticks are made from a tree branch called Beta. In fact, Beta's strength came from the root of a special tree called the SCALABILITY Java tree. Like a bamboo that builds a tough material through continuous growing, every branch of a SCALABILITY Java tree was very strong and could preserve the old flavor of HDF4 that can go bad quickly after opening. Beta branch was particularly suitable for building house on cloud because it was softer and lighter than the other branches, as it was not fully grown yet. Although Threads could not sort a large amount of food cans in table like Drill did, the strength of a Beta branch could open the individual food can easily. Although Beta was strong outside, Beta had a hole inside like a bamboo. Thus, Threads used the Beta's hole to create a food delivery pipes inside the house called open bag to share and deliver HDF to babies and elderly pigs in small batches. The third pig, Virtual, who studied at the HDF group, worked slowly but diligently to build a house with the same brick material called the C that the old mother pig used to fight the wolf. When all three pigs completed their houses, a huge dragon suddenly appeared from sky like a tornado. The dragon was 20 times bigger than the bad wolf in terms of scale. The dragon also had wings that could generate a polar vortex, a strong wind. The name of the dragon was TerraFusion. TerraFusion dragon first attacked Drill's house on the cloud. Drill's house with sickle haze and weak HDF5 glue was torn down easily. It was completely destroyed after a few minutes by the sheer volume of TerraFusion. Next, TerraFusion physically attacked Thread's house with massive body weight. Several punch holes started appearing in Thread's house. However, Thread's pig found a bug that created a hole in a beta branch and fixed it in an agile manner with a patch from another SCF Java tree branch. As TerraFusion could not destroy the house with kicks and punches, TerraFusion used its wings to attack the Thread's house with wind. It was partially successful with the cracks on the wall, but again, Threads patched them with another beta branch quickly. Ultimately, Threads' house could survive the TerraFusion's attack after the second patch. Finally, TerraFusion attacked Virtual's house. Virtual's house survived the ferocious attacks surprisingly well with very little damage. Since Virtual used the same C bricks and know-hows from the mother pig, the Virtual's house seemed robust from any attack, as it was proven by Wolf before. However, Virtual was much slower in recovery from the attack because C bricks were getting harder to obtain as an old technology. Virtual was thinking about adopting something new like elastic vinyl siding called HSDS or Kira, but was still suspicious about its durability. After the repeated failure of bringing down Virtual's house in a brute force manner, the clever TerraFusion dragon found one weakness in Virtual's house. During the attack, the dragon found that there's a secret key to the garage backdoor stored in Virtual's humorous backyard. Virtual's garage was connected to the main building by a bridge called VPN and a tunnel called SSH. The dragon stole the key, entered the Virtual's house, and blew up the entire house from inside with fire from mouth. TerraFusion looked for a similar way to destroy Thread's house, but the dragon could not locate any key. Thus, only Thread's house survived the TerraFusion's attacks. Threads wisely secured the main entrance using a new security camera called the role-based access control. RBAC cameras automatically recognized and allowed only pigs, not dragons, to pass the main entrance. After successfully defending home from several attacks, Thread's pig lived happily ever after inside a house on a cloud above the S3 land by enjoying all 5 layers of highly delicious foods from NASA. So that's it, folks. And I hope you learned something from the cloud version of Three Little Pigs story. Please find your own way to build your house in the cloud and enjoy the highly delicious food from NASA. Thank you.
Thanks, Joe. Thanks for bringing a touch of class to this session and also finishing way ahead of 15 minutes. So thank you very much for that. Any questions? For those who want to chat more about the stair presentation, I mean, I think that the Zoom session or something that can lead after this official session ends, so people may stay longer to discuss. But I haven't noticed any specific question regarding this presentation. And if someone has a question, please ask them now. Don't type in, or we are going to move to the next presenter. Okay, I hear nothing. So John, I think you're next.
All right. Yeah, I'm afraid my presentation will be a little pedestrian after Joe leaves, but I'll try to do the best I can with prose versus poetry. Let's see, let me share my screen. Okay, and the presentation. Alexander, does everyone see my slide deck?
No, I'm not seeing.
What's going on? Oh, I didn't press share. How about now?
Much better.
Good. All right. So, hi, everyone. I'm going to talk about HDF for the cloud, and specifically new features in our HDF server, HSDS. Let me see. So we're going to talk about storage schemas for the cloud. I think this might be a nice tie-in to Alexander's talk coming up next. HDF server features, what's new, and what's coming up next, and hopefully time for a demo. So let's start thinking about what HDF5 is. Okay, in my view, you can think of it in three different ways. As a C API, as a data model, and as a file format. So from the C API point of view, it's just a set of functions you call in the library that do certain things. From a data model point of view, it's this way that we've become accustomed to organizing data and metadata in a hierarchy. And from a file format point of view, it's this idea that I can share data by, say, sending a file to someone else, and that someone else is able to, pull out all the pieces he needs from that file. So let's imagine we keep the API and data model, but come up with a different storage format, right? And a format that will work well in the cloud. So for the HDF server, what we did is we created what I call a sharded schema. It's the idea that you take all the objects in the HDF5 file, the metadata describes groups or data sets, attributes, the chunks of the HDF5 data sets, and you store each of these as a separate object. And the idea is that we limit the maximum size of any object. And this is important in the cloud context because most object storage systems, when you modify an object, you have to replace the entire object. So we want to reduce any excessive latency or memory usage by not having objects, hopefully not larger than, say, 8 megabytes. Another advantage of this is that it's very easy to have multiple clients that are both reading and modifying the same file, right? Since your code files is organization of multiple objects, you can have different processes that are modifying different aspects of that collection, and they, for some care, they won't tread on each other's toes. And another nice thing is that you don't have the typical problem with traditional HDF5 files of managing free space. For example, say you have a file and you delete a data set. It's kind of like having your disk drive fragmented, right? You have holes in this file. So even though you've deleted that data set, your file size doesn't go down unless you recompactify the HDF5 file. with the sharded schema, it's the storage system that's going to manage that free space for you. So in this diagram, we represent a data set, and the heavy lines show the chunk boundary. And what we're showing here is that each chunk gets stored as a different object in our storage system. Well, there's a complication here in that when, say, I want to read this yellow rectangle, I need to read, in this case, 6 different objects and pull out the pieces from each of those objects that I need for my actual selection. So here's an example of what the format would look like. I have a root object, and inside that folder, there is a JSON object that has some metadata for that root group. And then under this, I have a collection of object IDs. Each of those has a JSON metadata. And furthermore, dataset IDs have 0 or 1 or more chunk IDs. So object2_ID has a dataset.json, and then like a 0_0, 0_1, so on, right? So in this case, that dataset is of rank 2, and we have a object3_ID is of rank 3 because I have 2 underscores. So if I need to access a particular chunk and I know the dataset's ID, I can index into that object by taking the dataset ID / and then the chunk index into that. So when you think about this, there's some niceties, right? So JSON is a widely understood format, and so without a great deal of effort, you could write applications that directly, work with this metadata. The chunk data, since the chunks usually comprise the majority of the storage, we store those as binary blobs for efficiency. Another obvious observation is that one HDF5 file can translate to lots of different objects. But since typically we're not manually dealing with these, that's not a concern. Another thing, maybe in comparison to ZAR, is that this is a flat hierarchy or semi-flat. If I have an HDF5 path like /G1 /G1.1 /dataset 1.1.1, that doesn't translate into this storage path. Instead, you would need to go to the G1 object, get its link from the group.json, and then get the G1.1 object from its JSON, and then finally get the dataset JSON from the dataset 1.1.1 ID. So this requires some more exploring of the objects. The benefit, though, is that we support we call it HDF5 multi-linking, in that you can have multiple paths to the same object. Also, it makes it much easier if I'm changing those links, right? If I directly map those links into the storage schema, if I renamed the link, I would have to move all those objects around. And another interesting thing is that this works equally well for object storage formats like S3, as well as POSIX storage. Okay. So it's nice we have this standard for a storage schema, but maybe you would like some software that actually read and write to that format. And that's what we created with the HSDS Highly Scalable Data Service. This was originally developed as part of NASA Access 2015. And since this NASA Access project ended, we've gone forward to enhance it and add various new features. And we have all the software is on GitHub. So let me just run through the basic features of the server. Clients interact with the server using the REST API. We have SDKs for Python and C. You're able to read and write just the data you need. We support compression. It's container-based, right? So you can run this in either Docker on a single server or Kubernetes or DCOS on a cluster of machines. And as the name implies, it's scalable. Data is cached, so recently accessed data you don't have to go back to S3. You can parallelize requests across multiple containers. So by adding more nodes, i.e. more containers, you not only increase the number of simultaneous clients you can support, but in many cases, individual requests are speeded up because we parallelize requests across multiple containers. You can have any number of machines that comprise your cluster. You support multiple clients, reading and writing to the same file or domain. And there's no limit to the amount of data the servers can utilize. Architectural diagram looks like this. So the blue and green squares represent containers. We have two types of containers. There's the service node containers, and they are the ones that front requests from the client. And then we have data node containers. They are the ones that work with the actual storage data. So on the right, we have an object store, which could be S3, or could be just a POSIX file system. And there's a virtual partitioning of all the objects in the object store. This is done by creating a hash of the object ID. So the aspect is that each data node, each object is owned by a specific data node. When a request from the client typically would go through a load balancer and wind up on one of these service nodes, the service node can determine which data node or nodes are needed to service a particular request. So the service node multiplexes these requests to data nodes, and the data nodes can read or write to a storage system. So this is where the parallelism comes in, because a request, say, to do a data set selection across 10 chunks, you can have all 4 data nodes working in parallel to read and write that data. Now, as we can scale this up or down, right? You can reduce number of nodes to free up computational capacity, or you can increase number of nodes to support either more clients or have more parallelism for your requests. So, so we've had the sharded storage format and a service that can work with that. But maybe you have actual HDF applications or libraries, and you would like to use all this new goodness, but you don't want to go through and change all your code to use the REST API. Well, we address this in 2 ways. For Python applications, we have H5PyD, which is a Python package that fronts the REST API. And for C and C+ applications, we have the RESTful. The RESTful is a HDF5 vol connector that lets you use the HSDS with the HDF5 library. First, let me talk about H5PyD. So H5Py is probably the most popular Python package for working with HDF5 files. H5PyD lets you use H5Py compatible code with the HSDS server. It's pure Python. There's no Python or calls to the H5 library. Beyond this H5Py functionality, we have additional functionality for things that don't really have a correspondence with the HDF5 files. For example, listing content folders, getting and setting ACLs, PyTables query interface. H5NetCDF and X-Ray can use H5PyD to work either with regular HDF5 files are with HSDS domains in the cloud. It's available on PyPy, and the source code is on GitHub. So I mentioned Xarray and H5.NET CDF. In the Python world, there's lots of different packages that are developed for different communities, and many of these are based upon H5Py. And the interesting thing here is that you can support this stack of libraries with either H5Py or H5PyD. For example, H5.NET based upon the file path, will use H5Py or H5PyD. So as a H5.NET or Xarray user, you don't need to worry about whether your data is local file or on the cloud. You can just dynamically switch back and forth.
15 minutes, John.
Okay. Let me skip through this faster. RESTful plugin, Lena talked about this a bit. Same thing, it's a plugin for the H5 library that lets you work with C applications using HDF. And the same way, you'll be able to work with files in the cloud without any changes in your code. There's a bunch of command line tools, and I'll show this in the demo. We support traditional HDF5 files. This is by linking to the actual chunks in the source files. Finally, new features. POSIX support. So now, in addition to S3 storage, you can have content in POSIX. Also, we support Azure, which means Azure Blob support for Azure Kubernetes, and Active Directory authentication. For not to neglect Amazon, we've added support for AWS Lambda, which lets you replace the functionality in those DN nodes with serverless calls to Lambda. We support Apache Mesos, the DCOS system. We have domain checksums and role-based access control. You can get all the details in that link. So now we have support a full spectrum of container management systems and storage systems. So this is expanded nicely over the last year. This is more about Lambda. If you'd like to try us out, you can go to this link and have a Jupyter Lab environment, which is set up for Kita, and try these things out. Things that we are looking at is, it'd be nice sometimes you don't want to go through a service. You would like to be able to work with clients that are directly accessing the storage system. And this is going to be the focus of our HS Direct Access project. So you can think of this as a new vol that works with the new storage schema, but without going through a server. Okay, and before questions, let me quickly run through a demo. So this is Kita Lab, and I have a notebook, and I'm going to run through an example. First, I'm going to try accessing a TerraFusion file. So Julie talked about TerraFusion. If I have this use H5Py equals true, I'm going to use what's called the S3FS file system to access this HDF5 file on S3. And if I get the ID, so it took 2 seconds to open the file. If I would like to see every item in this file, I can iterate through these. This is taking a while, so let me kill that. And now if I would like to open a data set, so you'll see it's a little slower than you would have for a local file, but not terrible. Here's the chunks. Here are all the attributes. I can do a selection on this data set, and I can do a plot. I can select over different orthogonality, and I'll do a 4 seconds here and do a XY plot of that. All right. Okay, so that was with S3 file system, and it's basically a low-level interface to the H5 library that's replacing each POSIX read with a equivalent S3 call. If I change this true to false, now I'm going to open the same content, but with a domain that's managed by HSDS. So, and let's remember, so these previous times were for the S3 file system, and the new times will be for HSDS. So it's faster to open. The ID, you notice, it went from a numeric integer to a GUID. If we try our visit again, it's quite a bit faster. So there's about 1,000 objects here. And that took 131 milliseconds. If I open the data set, so before it took about 2 seconds, it only took 140 microseconds because H5PD cached the content of that metadata. So it didn't have to go through the server in this case. Chunks is interesting because we are actually using this thing where we're not importing all the data, we're referencing chunks from the original HDF5 file on S3. So here's the S3 location, and here's this anonymous data set they're using to index into the HDF5 file. We can list attributes. So reading a selection from the data set took 500 milliseconds before, and now it took 139 milliseconds. And happily, we're seeing the same data either way. Now, taking this selection, it didn't align with the chunk layout, so it was a little slower than the previous selection. But with HSDS, since we can parallelize with all the chunk accesses, it'll be faster. And it just took 33 milliseconds. And we get the same plot. And finally, one more thing. I mentioned the command line tools. If I do, here I'm a shell. And let me make this bigger. So the folder this was located was here. And we're seeing that it's 16 gigabytes. I think Joe Lee mentioned doing the H5LS. We have an equivalent HSLS. So if I do that here, okay, so that kind of blew by pretty fast, but that's our 1,000 different objects. And you can do, there's a hsinfo command that will kind of show you kind of high-level stats for this domain. And a few things here. We have the ID of the root group. There's a scan time that kind of, it's a asynchronous process and server that kind of tabulates total storage used and such. There's an MD5 sum, right? So anytime you change any value in the data set or an attribute, this sum will change. So you can verify your content has not changed or not. The total size is about 16 gigabytes. The metadata bytes, now this is the data that we converted and stored in the HSDS bucket, is about a little more than a megabyte. Link bytes, these are bytes that we're linking back to the original HDF5 file, are 16 gigabytes. So the vast majority of the storage has stayed in this original HDF5 file. There's 929 objects, 60 chunks that are used directly by HSDS, and 250,000 or so link chunks. These are chunks that we're linking back into the original source file. Okay, so that's it for my abbreviated demo, and thank you for your time.
All right, thanks, John. There were some questions going on in the chat window, but I think Elena was trying to answer some of them. I suggest maybe you go through them now and answer to them. Or maybe,
Sure.
let's see, there's a new question, so you can see this one and answer.
Let's see, I can't get to.
Since this format looks cloud optimized, do we still need ZAR?
No.
Well,
No comment.
Okay. Well, I'll leave that for your presentation to discuss.
Sure.
Okay.
Okay. There's another one, I think, from R. Casey, if you see the next one.
How many servers running a demo in parallel? How much memory is used by those servers? So yeah, in my demo, I had 4 data node containers, 1 service node container on 1 server. The server had 16 gigabytes of memory. So you can use a lot of that memory as basically a metadata or chunk cache, right? So that if your, say, application has a hotspot and it's using less than that much data, eventually you'll fill out the cache and you won't need to go back and forth to S3. If you need more, you can get a larger machine or you can run a cluster using Kubernetes.
All right, then. There's only 4 more minutes on the actual session time, but I'll try to
There was one question about first demo, how file was accessed. It was through H5Py, right? On the server.
Yeah, H5Py plus S3 file system. So this is kind of like a Python version of the HDF5 S3 VFD plugin. It works the same way. It creates kind of like a virtual file handle and requests to read data get translated to S3 range get request.
So it was S3 VFD driver used underneath.
Not actually, but a similar technology.
Okay, thanks.
All right, then. Let's see. I'll share my screen now.
Oh, actually, our Casey had one example, one question about, are we seeing the effect of the cache performance? Yes, in this case, because I was practicing this demo just before this meeting. If you bounce a server, typically you would see
John,
these
can
first
you
requests.
answer that to him on chat window?
Sure. Yeah. Sorry.
No problem. So the last set, I'll be very quick. But there was this question about ZAR. Yeah, it's a very interesting question, obviously, and I don't have much time to kind of go into much details, but this presentation is actually talking about using ZAR API and HDF5 API to access each other's data. So at some point, obviously, it becomes an interesting question out of now essentially three software libraries, if you will, although they are data models, APIs, and the file format encoding like HDF5, NetCDF, and ZAR. Whether or not whether one API can work with the other 2 file formats as well, and things like that. So in this particular case, I'm going to talk about HDF5 and ZAR because it was it all started essentially. Let me see if this is going to move. Yes. So it all started earlier this year when we received some support from US Geological Survey to provide access to HDF5 files in object stores from ZAR Python package. And so when that was done and that worked, I said, well, how about going backwards and seeing whether or not we can actually have HDF5 API access to ZAR data and also in object stores. And so first I'll start with this work from going from ZAR API to HDF5 data, and everything I'm going to say is already being published. in a Medium blog in February of this year. So I'll be quickly going through this one. Although for this one, there is more results, just to make a spoiler. So the main, the heart of this implementation and what made this possible are two things. First one is we created a new ZAR store. As you probably know, ZAR has a number of backend stores. In this particular case, I call this one file chunk store. And the role of this store is to take the keys for ZAR array chunks and translate them to partial file reads of where those chunks are in a particular HDF5 file. And so the input for the file chunk store is another type of ZAR JSON metadata, which I also called Z chunk store, because everything in ZAR starts with Z's, like .z arrays, .z attributes, .z group. And so I thought, well, .z chunk store might be an interesting continuation of that trend. And so here's the little snippet of JSON, how it looks like. And basically what you see here is laser pointer. So here, what you see is a typical standard ZAR array chunk key that is generated by ZAR API, ZAR Python package. And instead of actually going directly to a ZAR backend store to retrieve that key, to get the value of that key, there is actually a piece of information that says, by the way, this chunk is this many bytes from the start of that file, and this is the number of bytes it's long. And these offsets and sizes are relevant to a particular HDF5 file. And so that's basically what the file chunk store does. And also there were little small fixes just in the ZAR and XArray Python packages that to make the separate ZAR store only for chunks to actually work. There was support, but it wasn't consistent, and there were some missing pieces in the code, but there was nothing major. The performance comparison, as published in the Medium blog and done by Rich Signell from USGS, are very actually comparable, and that was a very interesting finding. Like we see here that basically using ZAR, reading ZAR, it's about 24 seconds to do a fairly, well, I would say complicated, but aggregated statistical computation using Dask cluster, and basically took about 24 seconds. For ZAR reading HDF5 file, so we actually had a version of this ZAR dataset also produced as a netcdf4 file. And so ZAR reading that netcdf4 file and going for the same data using Dask cluster, so everything else was same, basically produced about 22 seconds. So it was very comparable, and the numbers were for a number of rounds basically stayed the same. So that was very, very interesting finding, and we all attribute that to essentially S3 being able to satisfy the number of concurrent requests that were going to that single HDF5 files. So we didn't hit that upper limit. And so that's, I think, what was the key in actually working. Want to try it out? We have, you need a number of things. For your HDF5 data and your HDF5 files, definitely you need Python, obviously. You need the HDF5 1.10.6 library. You need to install HDF5 from the master branch. This capability in HDF5 to produce necessary information was added in October last year, but for some reason there is still no unofficial release. Although I would say, I think to recall that the Conda Forge channel in Conda, I think supports an H5Py package that actually has this feature. But still, if you can install from the master branch, that would do it. And also, there are two more. You need to install XArray and ZAR Python from these forks of XArray and ZAR packages for now. The work seems to be close, that both of XArray and ZAR officially support these fixes that I mentioned earlier, but I'm not sure that it still all went through. And also you need FS spec just because we were using it. And the piece of code that you really need for your own HDF5 file is this HDF5 to ZAR translator. And it's available at this GIST. We still haven't decided where to keep it, so it lives as a GIST, but maybe eventually will be moved in some other repository. And so limitations, the one that I became aware 2 days ago is that actually there is a HDF5 data set can be laid out in a file in 3 different ways. The most popular and used ways are contiguous and chunked. There is a third one called compact, and unfortunately for that one, HDF5 library does not provide information of the byte location and byte offset and size. And as it usually be, 2 days ago I learned that there is an ISET2 data product, at least one, maybe more, that actually uses this dataset compact layout. So that would make those files actually not usable this way, not yet at least. The other possibility is that HDF5 library or dataset data is compressed or with some other compressor that ZAR does not support yet. So that's a possibility. But if you stay within the logical ones, that should be okay. And the storage system where the HDF5 file has to support partial file reads. In this particular case, we used S3, which lucky for us supports range gets, so all worked. But that's one of the requirements as well. And so this ends the ZAR to HDF5 data. Now we switch back to the HDF5 to HDF5 API to ZAR data. And this is fairly new development. It's embarrassingly close to this session, so I don't have no code to show you or anything that you can try out immediately, but we found technical way to do it. So we'll continue following this, and hopefully within the next month, we'll have something more definitive to say about this. So this is now essentially having HDF5 API going to ZAR data. So I tried to use the exact same ZAR data set that used in the previous work I mentioned, now accessing from HDF5. And because this ZAR dataset is in the S3 and it's in this distributed ZAR format, the obvious choice for me to use was the HSDS that John talked about in the previous presentation. Right now, we are using only ZAR data in S3, and also the way why HSDS can have access data to ZAR is because essentially HSDS's sharded schema is very similar to ZAR's. There is a combination of JSON and binary objects, and so it's essentially just a matter of producing the correct HSDS metadata for ZAR metadata and then providing links to ZAR chunks in ZAR chunks object in S3. And this is, as I said, still work in progress. So very briefly, how it's implemented. John, I think, in his Jupyter notebook showed this, but essentially HSDS schema introduces a new type of chunking, which basically is called indirect chunking, chunked reference indirect, which means that chunks live somewhere else as links in some kind of backend storage. This chunking layout is not supported by the HDF5 library right now because obviously it's not applicable to the file format and the standard file format that the library currently works with. And I'll skip over these things. And coming to these last 3 bullets, we tend to be a bit more thicker HDF5 information. But the crux of it is that we're using an anonymous HDF5 compound dataset. That's a feature in HDF5 that not all datasets need to have a name. So this one is sort of like a silently present. That's where we store the information. And the compound data type has 3 fields: byte offset, which in this case of the ZAR array chunks is always 0. We want to start from the first byte of each ZAR array chunk. The chunk object size, which is going to be the size of each ZAR array chunk, and then chunk object URL. And then the actual HDF5 dataset that represents the ZAR array specifies this new chunk layout, and its value points to the anonymous HDF5 dataset with chunk location information. All of this information is really not that anyone who is the user of HSDS needs to worry about. HSDS does this thing in the background, and the people still get the exact same data. We verify that we do get the same numbers, so we're pretty certain that it's working. There was only one more step that I needed to do, and that is that HSDS right now does not support the BLOSC compressor, which is a very popular and common compressor for ZAR arrays. And so I had to actually do one intermediate step to actually copy the original ZAR data set and change the compressor to zlib, which is the gzip or deflate that HDF5 library supports. And here's the piece of code that I used. It worked immediately. I was really impressed. And I'm usually familiar with people using Xarray to do any kind of copying from ZAR to ZAR or something like that. I actually used only the ZAR original tool, which is this method called copy all. But I was really impressed how it worked, and immediately did recompress the data from BLOSC to zlib, and I got my working copy of the ZAR dataset. And so here's the very simple how these things look like. On the left, we see the Zeta ZAR array, which is in that ZAR array dataset. It is a float 64, the size, the shape, and the chunk sizes. It's about 49.5 gigabytes. And on the other side, I wanted to show information of this anonymous HDF5 dataset that holds the chunk information. As you see, its shape is much smaller than the original Zeta array because this one only holds the chunks, not every element. And its values here printed as a NumPy array show you the byte offsets, which is, as I said, always zeros. The second field is the byte, the chunk sizes obviously vary. And here comes the chunk array URLs to S3. And that's how basically it all works. The limitations, the only one right now that we see is really the compressors and filters that ZAR array data uses that maybe HDF5 can't, or not supported, but HSDS. But I'm hopeful that that's not really a problem because both the ZAR Python package and HSDS are Python applications. And so I think it should be possible for us to support the ZAR's numcodex package. And so HSDS should be able to decompress the ZAR data. And that's basically it. I'll stop sharing now and see if there are any questions. How do I know? Let me see. All right, stop sharing now. Sorry, I have to go through questions, but is there any question now? Let me see quickly. Regardless of formats, okay. John Reedy, yes. Answers. Yes, presentations will be uploaded to the Sketch. Ethan, have form. Yeah, the HDF5 to ZAR. Yes, doesn't modify the file. Yes, it's all read-only. And RKCS questions. Could ZAR as a metadata reference to an HDF5 volume be used to uniformly access different flavors of HDF5 data, netcdf, ASDF, PH5, etc.? Yes, that's very interesting. I think that really when you start breaking files into binary objects for chunks and then whatever text representations of those chunks and user metadata as attributes, and again, your case is really read-only. I think that there's a whole universe of opportunities to basically have all kinds of software support, all kinds of accesses. I think it's really just making those connections. And again, unless the compression, the data is compressed and other things. As far as the HDF5 data model, we still don't see any other data model API or format that we don't think, or we doubt that HDF5 would have problems representing. In other words, we think that HDF5 could really deal with all the others, file formats and APIs and data models for data cubes. And that's basically all I have. Sorry about this almost 15 minutes running over, and I wish to thank everyone who stayed this long. And as I said, we'll upload the slides, and also any questions you have, info@hdfgroup.org is probably hdfgroup.org. Yes, that's probably the good starting point, and someone will find the right person in the company to answer the question. Thanks, everyone.
Hey, also, if
Thanks,
I could
Alex.
ask any of the organizers and speakers to put some takeaways in that document in QQ chat before you all take off.
Okay. All right.
That'd be great.
We'll stay later. All right. Thanks.
Thank you very much.